Welcome again. In this presentation, I will introduce the concept of internal model principle. I will state it, verify it, and point out the important aspects of it. Let us consider this closed loop system where we have the plant G, controller GC, B by A is the transfer function, SC by RC is another transfer function. The time domain signals are indicated by smaller case, lower case letters. When we take Z transform of those, we will replace them with uppercase. So let Rz, which is the Z transform of R, be a ratio of polynomials. Similarly, the Z transform of the disturbance signal V is written as BV by alpha V AV. Each one is a polynomial in Z. Now suppose this polynomial alpha R and this polynomial alpha V have zeros on or outside unit circle. For example, if there is a step change, then you will have a Z minus 1 in the denominator. In that case, alpha R will have Z minus 1. Suppose it is a ramp, then you will have Z minus 1 whole squared in the denominator of capital R. So this alpha R is Z minus 1 whole squared. 0 on the unit circle is also an unstable one, outside also is unstable. So all of those are grouped under alpha R and alpha V. Let alpha be the least common multiple of alpha R and alpha V, that is, it has all the zeros on or outside the unit circle. We assume that there is no common factor between alpha, which is the least common multiple, and the numerator of the plant B. We want to find a controller GC for servo or tracking problem, that is, this Y has to follow reference signal R, the set point R, and regulation, which is the rejection of the disturbance V that comes here. We need to find a controller GC that will help achieve this, and there should be no error in these two. Okay, let us state the internal model principle now. We can show that it is possible to find a controller GC of Z for servo problem or regulation problem if RC contains alpha. Remember, alpha is the least common multiple of unstable poles of R and V. So I have replaced RC with alpha times R1. This alpha has the unstable poles of V and R. This is the internal model principle statement. We will verify these. Let us construct the closed loop transfer function. Let us write down the expression for Z transform of Y of n, which is capital Y of Z, which is equal to the product of these two divided by 1 plus once again this product. So that is the transfer function between Rn and Yn. So I put R here, which is the Z transform of this small r of n, the reference signal, plus the transfer function between V and Y, which is given here. The forward gain is 1, so you get 1 here, and then the denominator term is the same as what you have here, times capital V of Z. I am not putting R of Z and Z, I have not put. Let us simplify this. Okay, it is easy to verify this. Similarly, you get the second term here. Okay, let us start with that expression and let us see what happens in the regulation case. In regulation, we take R equals 0. You want to see whether the disturbance that comes through V gets rejected. So let us substitute for V. Remember, this is the expression we choose for V. This alpha V has some zeros that are outside the unit circle or on the unit circle, and this alpha, which is the LCM, contains this. This is what we have claimed. Now suppose alpha contains the unstable portions of V which comes through alpha V, then they will get cancelled. So if we cancel it and then choose SC and R1, of course R1 alpha is RC, can choose RC and SC such that this denominator term has its roots within the unit circle. It will be shown later when we discuss control design methods such as pole placement. So we have verified the regulation problem. What it says is that if this alpha contains the unstable part of this V, then it will not appear in the overall expression. That is achieved by cancellation of those factors given in blue here. So what is in red will be required again. You may want to write this down. Okay, this is that expression. Servo problem is obtained by V equals 0. So let us take V equals 0 and we want to check whether this Y will track R. Now let us substitute for capital R. Before that, let us substitute in this expression and find the error between the reference signal or the set point and the actual output Y. So when I multiply this, I get R. The second term is obtained from here. Let us simplify this. This SCB will cancel this SCB. So I get this R1 A alpha in the numerator and you get this expression for capital E. Alright, this is the expression for servo. Now let us substitute for capital R, which is the reference signal, which we have said contains Z minus 1, Z minus 1 squared and so on and so forth. Essentially factors that have zeros on or outside the unit circle. But we have taken that this alpha contains those, it will cancel those factors on or outside the unit circle. And once again, by choosing RC and SC, we can make sure that this factor has roots within the unit circle. Once again, it is through pole placement, for example. So we have verified the servo problem also. The internal model principle, to summarize, is that unstable poles of V and R appear in the loop in the controller as a part of its poles. Let us conclude this discussion in this slide. Unstable part of external signals should be present as poles of the controller through alpha. It is important to note that the unstable part should be known exactly, so we can cancel them exactly. It cannot be an approximate cancellation because these are unstable. If these are only approximately cancelled, then there will be a lot of problem which will be discussed later. It has to be cancelled exactly. What if it is unstable? We know that the signal is going to be unbounded, so you have pole outside the unit circle, but we do not know it exactly. Unfortunately, we have no theory that can handle that situation. No theory exists for unstable but unknown poles. And as mentioned earlier, this factor has to be stabilized separately. Internal model principle generalizes the system type. For example, when we say that the unstable portion here, let us say step signal that comes through here, will require a Z minus 1 here, so that it can be cancelled. So these are the ideas one sees in the topic system type. So one can say that the internal model principle generalizes the system type. We will use this concept when we design pole placement controllers. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.